Welcome back. Hopefully you enjoyed those exercises. If you did the exercise with the frequency analysis, then you should have obtained a histogram that looks something like this. If you compare it to the previous two we did, you can see that Vigenere cipher does indeed suppress the frequencies. So the peaks where the E occurs in these cases are not so obvious. And what we're going to find out is the longer the keyword you use, the shorter these peaks become and the flatter the distribution becomes. And it's important to recognize that Vigenere is a symmetric cipher, meaning we're using the same key both to encrypt and decrypt. The algorithm is simply for you encrypt each letter from a different alphabet, cycling through the collection of alphabets that are being used. And the keyword zebra is used to pick the alphabet. So the key is actually both the table of shifted Caesar alphabets plus the keyword that's used to select which alphabets are being used. The Vigenere cipher was called the unbreakable cipher because it thwarted frequency analysis, and it was not broken for over 300 years. So it was quite a strong cipher historically. That was 300 years of happiness for Alice and Bob and sadness for Eve, who could not break messages encrypted with Vigenere cipher. But wait, there's a problem still. Let's try Vigenere cipher on this message. And let's use the keyword zebras in plural. If you do that and you plug it into the tool, what you'll get out is the following message. And what you can notice about it is it's got some letters repeated. So SLF is repeated 3 times. And the distance between these two repetitions is 6 letters, and the distance between these two is 18. Similarly, the UAQ segment is repeated twice, and the distance between it is 18 letters. JMP is repeated twice, and the distance between it is 12 letters. So, as you can see from those examples, the gaps between these repetitions are all factors of 6. That's the key to breaking Vigenere cipher. Because the gaps are all factors of 6, we can guess that 6 shifted alphabets were used to encrypt this message. Because of that, we can now break the text into 6 separate messages and do brute force or frequency analysis on each of the 6 portions of the message to recover the original message. Don't think that this type of repetition occurs only in a rigged message such as this one. It would occur in any encrypted message that contains a sufficient amount of text. So this was a way to break the Vigenere cipher, which wasn't done until Charles Babbage first did it in the 19th century, and then Frederick Kaczynski did it also 10 years later. So Eve wins again. The Vigenere cipher is breakable. And the problem with Vigenere is there were patterns that could still be analyzed. We couldn't completely suppress the frequencies and the repetitions. Can we get rid of all the patterns? The answer is yes, and here's how. Let's consider this message again, but this time let's create a random keyword, place the shift numbers above the letters of the message, and encrypt it again. We get the following encryption, where you see there are no repeats. This is an example of perfect secrecy, provided we use the key just once. We use this random key just once. This is called the one-time pad, and it was actually used as an example of perfect secrecy. To summarize it, it's a perfect cipher that cannot be cracked. It's been proved to be perfect, provided it has the properties that the key is as long as the message and created randomly, and the key is used only once. So the way this cipher would be implemented is Alice and Bob would each have their own pad of keys, and they would, when they want to encrypt a message, they would choose the top key in the pad, encrypt the message, send it, decrypt it, and then destroy the key. Next time they would use a different key. But I think you can see that this cipher comes with some issues. It's not very practical because you have to distribute pads to everyone that you want to communicate with securely. How do you get the key from Alice to Bob? Different approaches have been taken, but they're all vulnerable to attack of various sorts. So this, even though this is provably perfect, it's really only been used successfully in the case of the hotline between the United States and Russia, where we have armies to protect the keys as they're being transmitted from the US to Russia and vice versa. So this is known as the key exchange problem. Even though we can have a perfect cipher or a very strong cipher, Alice and Bob still need to share the key, and Eve is always listening in, trying to grab the key. So that leaves us with this question: how can Alice and Bob share a secret key without Eve getting it? Unless we can answer this question, we really can't have an internet where we can encrypt our credit card transactions every time we want to buy something on Amazon. We're going to have to look at this question and see how to solve it. And that's for the next lesson.